about the fusion method.
Thanks. So, let's see what everybody sees blue because I had some problems with. Yeah, is it good or shall I take a red marker?
Better than most.
There's maybe a thicker blue. Okay, good morning, and it seems that the organizers, and you should realize that the organizers are really Ben and Rahul, and I did very little. The organizers organized the morning of nostalgia here. Most of what I'll talk about today, so the title is the fusion method. For proving lower bounds, obviously, that's what the workshop is about. Most of the papers I'll talk about are, before many of you were born, like 35 years ago, and so, and then I think Or will talk about papers that are maybe only 30 years old. So we'll make progress. I'm basically going to read from a survey paper I wrote in '93. That summarizes this method and the papers related to it and how it evolved and how it became something I believed at the time was a very valuable tool for proving lower bounds. And somehow, just after the publication of this paper, there was nothing else happening. So maybe the mistake I made, this paper was presented at the Erdős 80th birthday, where most of the audience were combinatorialists. In fact, there is a lot of I was hoping to get them involved because there are lots of beautiful combinatorial questions coming out. That didn't happen. So anyway, I decided now to try to excite people who really come to do lower bounds. Yes, Russell?
Okay. The first time I heard of the fusion method was there was a paper by Razborov showing that the fusion method didn't work.
Yeah, of course. Yeah.
So this was not encouraging.
Yeah. There's a bug in this proof,
Oh no, I didn't know.
Yeah. No, there's no bug in any of Razborov's papers, but it's not the statement. I'll try to convince you, of course, why it's still useful and give you some concrete open problems. So let me tell you about this bit of nostalgia. So the 80s were, in some sense, the optimistic era of lower bounds. And suddenly, out of the blue, lots of papers started coming out. So I'll just say, of course, it's not going to be an exhaustive survey, and many things I will not mention, but I want to mention things that will be related to what I want to talk about. Around 83, both Aitai and first Sachs and Zipser proved that parity is not in AC0. And that was a big thing, and of course it was not just a big thing in itself, it was also an introduction, at least demonstration of the power of the random restriction method. Of course, this class didn't exist before this paper, so it was not like solving a long-standing open problem. They motivated it, as many of you know, from understanding the polynomial hierarchy and so on. But then Razborov came along. I mean, he was still a student in Moscow, and proved that clique is not in monotone P. And this was a really big deal because this was open for, since Shannon proved in 48, earlier, maybe in 1940, this master's thesis about Boolean complexity, that most Boolean functions are difficult. The problem of proving a circuit lower bound was open, explicit circuit lower bound was open, and people quickly realized, both in the West and in Russia, that even the monotone case is interesting, and worked on it. I mean, there were a lot of work in this 40 years, and Razborov proved it, and he proved in another paper, but the same thing. He proved also the perfect matching. The perfect matching problem is also not in monotone P, which is even a bigger deal because it's a function in P. It cannot be done by monotone circuits. And in this, he also inaugurated what we call the approximation method. That was as you'll see, the fusion method is trying to capture and generalize. And then people got interested because of this result. What can you do with the constant depth circuits which do have parity gates? What can't you compute with them? And I mean, there was some frustration, and then somebody sent word to Razborov that this is open, and he responded, yes, all my R's will be Razborov in this talk. There are lots of lower bounds by Ran Raz that I'm probably not going to mention, so there will be no confusion. So Razborov proved that if you look at majority, for example, it is not in S0 parity gates. And this already you cannot do, or at least we have no idea how to do it with random restrictions, because parities don't care about random restrictions. So he showed that this too works in the using the approximation method. So, and then, ever since this first paper, everybody got extremely excited. We are so close to proving that P is different than P, right? I mean, that proving super polynomial low bounds for circuits, you just have to tweak somehow the approximation method to take care of the NOT gate. And there were lots of attempts. In fact, some of you know, those who get, like me, lots of P different and NP papers to referee, and P equals NP papers to referee. There are still people who send papers that are just based on just trying to tweak this into lower bound for non-monotone circuits. So after a few years of attempts, Razborov decided to put everybody out of their misery, and he wrote another paper around 89, where he really clarified the situation. So he said that, first of all, this approximation, it's called something on the approximation method, this paper, and he explained that these lower bounds here are actually the pure approximation method. Pure approximation method. And in this he said that pure approximation method basically cannot prove any non-monotone circuit lower bound. So can prove has basically an upper bound of something like on n squared on, has an upper bound on non-monotone circuits. They cannot prove non-monotone. This is pure approximation. But he also introduces a general approximation method, which can prove tight lower bounds. So it can. So, he didn't need to go to the fusion method, which is basically a fancy version of his. He proved that it can prove. So the general approximation can prove tight non-monotone. You just need to try to do it. And
Where does Smolensky come into the picture?
so Smolensky comes into the picture. I will say a few words about this when I want to elaborate a bit about this. Yeah, I'll explain what Smolensky. But this was the Razborov result, and I'll say this in a second. And just to prove that the general approximation method can do something. Please feel free to ask questions. And
you say the general approximation can prove tight lower?
Yeah, tight lower bounds. Yeah, I'll explain this in.
Does he show it can, or
Can.
no barrier?
It can prove tight lower bounds. Some methods of proving these lower bounds are natural, and these will not work. But the method I'll explain. Just give me a few minutes just to end with the nostalgia here. He proved he showed another result where he applied the general approximation method to branching programs, to non-deterministic branching programs. So he proved some non-deterministic lower bound, more or less the majority, requires sort of a non-deterministic branching program size of majority is at least something like n times log star. So it's a big deal, and especially because it uses the same approximation, the general approximation method. And then Maurizio, the paper that led to the fusion method was a paper of Maurizio Karsmer around, I don't remember, 92. There are various versions. We basically try to understand Razborov's method, general approximation method, better, which is what I describe as the fusion method. So he reproved the monotone circuit lower bound of Razborov and did more that I'll tell you about. So this is really the beginning of the fusion method. And we wrote a couple of papers, Maurizio and I, around 93. One on non-deterministic circuits. And we wrote another paper on span programs, and I'll try to explain how this is related. So one of the points I want to make is the fusion method is not just a lower bound method, but it's also a method to define new computational models and to characterize complexity classes, span programs. And one thing more that I want to say about Karsmer's result is to point out that this history is even older, and he connected it to works of Sipser, from around between 80 and 83 or 82. Maybe one is unpublished. So works of Sipser, which prove lower bounds on countable circuits. So I'll say what they are. Then this, he proves basically the result that an infinite parity cannot be done in AC0 in countable circuits, which for topologies is a Borel set. And he proves in the other paper that basically NP infinity is different than ONP. Infinity, which for topologies or set theories is that the analytic sets are different than the co-analytic sets. Some may know that this result was what got Sipser. I mean, that sort of helped him develop this really AC0 lower bound. And this attempt, I think, kept him busy with for 10 years trying to find a finite analog of this, which would be NP different co-NP. So I want to tell you about some of these results, and so questions. I mean, it's just a historical account, which is, I guess, slower than I thought. The questions, yeah. I want to tell you about the approximation method as was understood from these papers, and then I want to explain how the fusion method views them. And I'll mention the Smolensky. So for those who know the approximation method, and I hope that all of you here, people trying to prove lower bounds, we have like 3 or 4 techniques. Maybe I should mention, I mean, this history, there are other methods, which I maybe should have written down, or we'll talk about it. Maurizio Kaufmann and I proved, maybe this is worth putting something here, like in 88, Maurizio Kaufmann and I proved a different monotone lower bound using a different method, namely that ST connectivity is not in monotone NC1. And the reason this was interesting, despite Rasbour's result, that this is a problem in monotone P, where these guys aren't. And this was another method, which is a communication complexity method. Communication complexity. Sorry, another method. And I want to mention these methods, and there are other methods. Rasbourov sort of extended this result, or we proved this result using what he calls the rank method, and which actually found recent applications in some of the lifting results and so on. I want to explain the approximation method in the way it was presented in these papers, and then to explain in what way it's different when you view it as a fusion method. And all these methods, at the time they were written down, were understood as taking a progress measure. In the way we do almost all lower bounds, defining a very clever progress measure and see how a small circuit, is unable to make quick progress towards a complicated function. So these guys were sort of bottom-up proof techniques. This was more top-down proof techniques, but they were both sort of dynamic with the structure of the computation. So let me describe just how the approximation method works, and then describe the fusion method in more generality. The idea is that you have a circuit. It's a circuit C. It's supposed to compute some complicated function f. And the circuit is small, so C is small. And f is complicated. You want to say that this cannot happen, and so you want to say there are too few gates here. And we know Boolean circuits are really complex objects. And Rasbour's idea was that you will take whatever operations here are at every, can be AND or whatever operations or arithmetic gates, take the gates here and replace them by simpler gates, simpler to understand gates, and create an approximate circuit, C prime, in which the gate is approximate. And so that if you have your two functions, g and h, in the circuit, here comes g op h. When you look at what comes out here when you plug g and h, what comes out, it's similar to h. It does not make too many errors. And I will stress, I probably will not say it again, counting errors doesn't have to be just counting how many inputs it differs. So maybe you want to put a probability distribution on the inputs and look at those that are very interesting to this function. And this thing computes some function f prime, and you want to say that, so here you make small errors, few errors I should say, few errors but this is not at all close to the function you want to compute. So if you make few errors per gate, there are few gates, you get something and it's far away from the complex function. The original circuit could not have produced this. And this number of errors sort of computes for you, this progress measure. Basically what you want to say is that, so when I say few errors, what I mean is that G operation H is very close to G. Okay, on some distribution. That there are very few differences according to some probability mass. And now I can tell you a bit more about what happens in these two papers. Just to say what are these approximations. So in the monotone circuit case, in the clique or perfect matching, not in monotone P, so n goes to approximate n, and O goes to approximate O, as you can imagine. And the point about this, and the point also in the other result, which is that majority is not in AC0, 2, is that it's more than just approximating the gates. What you really are doing is looking, instead of looking at all Boolean functions that are potentially computed in this circuit, right? You start with, maybe the variables x1 through xn. There are functions on the Boolean cube, they are the simple functions, and now you're trying to compute from them complex functions. So potentially you can compute arbitrary Boolean functions here. Once you introduce these approximate gates, they leave you in a closed subset of the Boolean cube. They don't allow you to step out of a set of simple functions. And the simple functions here, so these are the gates, I guess. And the simple functions. Here they were just, for those who remember, these were just disjunctions, so O's, so small, yes, I should say, small disjunctions of small cliques. You just maintain, you just demand that everything computed in this circuit is always small disjunctions, small cliques, and when something which doesn't look like that is computed, you just kick it so that it becomes one of these, and then you make some errors. And in this, of course, here they are, these are all binary binary gates here, but sorry, yeah, they're all binary, but this is, sorry, that end looks like this. Here the gates are arbitrary fan-in. And so this parity just remains parity. And the end is going to, I should have probably done it in reverse, goes to a parity of small ends. So this may be loud, but here you have ends and they are few. So basically, the approximation here, the simple functions are low-degree polynomials. Okay. And you remain within low-degree polynomials. To the question that Or asked, there's a big difference between these in many ways, I mean, between these two proofs, but they are both approximation methods. The difference, the technical difference is that here, the real difficulty comes to proving that these approximations make few errors. This is heavy combinatorics. Once you've done that, to see that simple functions cannot approximate clique or perfect matching is easy. Here it's sort of the opposite. To prove that the gates don't make many errors is very simple. And then to prove that a low-degree polynomial cannot approximate majority is not so simple. I mean, it requires an argument. So Rasborov does it in a certain way using linear algebra. And what Smolensky does, the only change in Smolensky, he takes the first as is, the first part of Rasborov as is, and then he's finding another way of showing that low-degree polynomials cannot approximate other functions, and because of this, he was able to, if you want to add here Smolensky, you can do mod 3 gates cannot be computed by AC0 circuits with so he changes he adds in the second paper. But he took Rasborov's paper and just found a different way to argue about that. Yeah, today we clapped them as one result, but that was the order and that's how it happened. Okay, so summarizing this, the approximation method gives you a progress measure. You have to still be clever in finding it for different types of circuits, and then you argue that every gate at a time does not add much to to the number of errors, does not make too many errors. At the end, you get to something that cannot be approximated by click, therefore the size of circuit must have been large. Okay, so the fusion method, which is starting with the Maurizio Karchmer, is a different view of this. And this view, I should say, it appears already in Rasborov's general approximation method. I just like it much better, and then we sort of understood it much better even after doing these extra works. And it says the following. So this is like the key thing for the talk, is this picture. So first of all, we are just going to consider straight line programs. That will be our view of a circuit. I want to think of it as a sequence. Okay, so you start with, we have some model, it has some operations, and we start with the straight line programs. How does a straight line program look like over some set of operations op? We have the various operations here. We start with the variables. And these are, we can think of them as G1, G2, Gn, and then there are more functions, Gn plus 1, Gt. T is the size of the circuit, so we sort of assume T is small. That's what we want to contradict if it computes some complex function. And there's a sequence of functions, very important. We think of it as a sequence of functions. And then we see that we just look at the computation on every accepting, every accepting computation. So f is some Boolean function. Everything I'm saying will work for other domains, but I'll stick to Boolean here. It's a very general method. So we can plug one of the functions. There may be one. Maybe that's the 1 of f. So here we are going to put, it's a big matrix. Here we are going to put the ones of f. In fact, we don't have to put all of them. We can take some subset of our choice. So this, you'll see, this is very flexible in general. So we pick here some one of the functions, then we see what, what. But the last guy is 1, right? This is supposed to be f, and then we take another one. But the last guy is f, and so on. So many. Now you'll start seeing that one of the problems with the method, or maybe with the problem with low bounds, is that this is a very big and complex space, already exponential in the number of variables. And here is the crux of the fusion method. So we look at this matrix. And what we are trying to do is to fuse them into a computation, into another computation, a sequence of length t, just like before, right? Where this part, the input part, we get some input z, and f of z is 0. Okay? On the other hand, this produces a 1. This computation produces a 1. And here there are things that hopefully are legal computations in that, in this program, starting from here, you know, G I is going to be G, no, Ji operation I, G Ki, right? Where Ji and Ki are less than I, and I is bigger than. Right, so normal gates of a computation, you compute things, or otherwise they are just variables. And you hope that the sequence you have created respects this. Okay, so how are you going to generate this sequence? Well, you just map in an arbitrary way, I mean, with all the freedom in the world, to fuse them into this computation. So what are you going to do? You're just going to pick. So there's this space now of functions on U. So we have all the, you know, you can look at omega. Again, maybe a subset of all functions on U. F, 0, 1, 0, 1. So we take such an F here, on every column, F. And apply it column-wise to this table. Okay? So when we take such a function, we get a 0, 1 sequence. Right? So the question is, can you hope that this, what you are trying to do will happen, namely that it will create a legal computation which takes a 0 of the function to the output 1, by which you would have proven a contradiction, namely that t is too small to compute f. Right? So let's see what should happen. What are the magical properties that f should have? You can pick any f you want. Right? What are the magical properties that will make this work? Well, they are obvious. So what are the properties that should make it work? So one, maybe the most trivial one, it should respect the all ones vector. It should respect, or in fact should respect the constant. So f of 0 is 0, f of 1. Oh, that's easy to restrict yourself only to such functions. The second thing is you want to generate a 0 of the function. Right? So what you want is that for every I, f of xi is the I. And nevertheless, this z is the 0 of the function. Okay, so it's clear what I'm writing here. Xi is a function, right? Xi is a function. And now, it's a function not on the, it's a function on U. Okay, so, here I always write, the first variable of some one input of the function. So you should view all of these guys as Boolean functions of U, and xi is just this function, yeah.
Is it important to have the same function for every column?
Yeah.
Okay.
Yeah, although you could imagine trying to do something with, but it's important for the way I'm going to do it, definitely. Yeah, okay. So you want to generate a 0, and the last thing, you want consistency, right? So what's consistency? You want that the operation f commutes with the operations of the circuit, with the gates of the circuit. So the third condition is that f of the operation h is h for every g and h. Every g and h appearing here, but we don't know what will appear here. We don't know what Boolean functions. So they are Boolean functions, and we restrict them to this subset U. So, but you should think about them as just Boolean function on n variables, like the xi. Okay, so, if those three things happen, right, if this happen, if there exists, so let me summarize it here. If there exists such an f, if f satisfying 1, 2, 3, size of f. Size using this operation. Sorry. Okay. Everybody is happy with this. This is a plan. I mean, so if you manage to do this somehow, yeah.
So could you have a probabilistic version where you had a probability distribution on F's and the third condition only held with high probability?
Yeah, the way. No, I don't know that. You just. I mean, if it implies the existence of an F which satisfies all of them, then sure, yeah, you can attempt a probabilistic argument to.
Well, so you say because G and H, you don't know that G and H. You don't know what G and H are, so you have to have it for every
yes.
G and H. But if you say for every G and H, with probability more than 1 minus 1 in 2t.
Yeah. Yeah. So that. Yeah. So what you're saying is that here is a specific way of proving the existence. Yeah. Any way of proving the existence of such f is legal, including a probabilistic argument. Sure. But I'll say something why probabilistic arguments, if I get to where I want to, I may say why it probably is not a good method. Yeah.
Why do you want f of the zero vector to be 0?
Yeah, you don't have to, but yeah, that it makes sense that they will respect constants. There are various things I will not say, but yeah. By the way, for those of you that this reminds polymorphisms, if you can, yeah, I wish there was a more concrete connection, but definitely. Also, this combination of fusing should remind you of polymorphisms in the study of CSPs and the dichotomy conjecture. I'm not going to go there. So, you know, does there exist such an F? That's a question. So, but the point is that we can define, you know, two of these properties are very easy to satisfy. We just mandate them. We mandate that it preserves constant, and we mandate that it generates a zero vector. Right? So in fact, we can define omega f. Omega f is which depends on the function. It's just a collection of all f's in omega, such that f of 0 is 0, 1 is 1, and f of x, so it's a vector of n variables, is in f inverse of 0. Right? And now, if there was really a circuit of size t computing it, then the third condition should be violated for every f. In other words, the set of tests here should cover this space of f's. Right? We must have, you know, if size of f is at most t, it means that for every f in omega f, there exists g, h, and an operation, a legal operation, such that f of g, h is different than f. Right? So we can define a cover problem. We can just define a cover problem where this is the set, this is the space we want to cover, omega f, and the subsets of this space that we want to cover it with are those sets. So if you think of G, H, and operation, a legal operation, as a collection of all functions, such that just basically satisfying this, then we can define rho, and rho depends on some model of computation. Model of computation, for example, includes the operations you are taking into account, and we'll see a little more things you can do with the model here. But anyway, this is just a collection of maybe I'll just call it the family of subsets that I want to cover it with. I'll just call it M. It's just a collection of all these sets, G, H are Boolean functions. And the operation is a legal operation in our circuit. And it defines the cover problem, right? Rho, which depends on omega and depends on this model on F. I'll just call it rho of F. Is just the minimum number of such sets that cover the universe. Then minimum T. That we have, G1, H1, of 1, dt, covering omega F. Right? So we have, we provide in this cover problem whose solution lower bounds the circuit size. And here is so this is a meta theorem, right? So basically, meta theorem 1. Size, and it depends on the model, of F is at least rho omega model F. And you see that omega could have been chosen, I'll talk about it in a second. Omega could have been chosen, and okay, so you get a lower bound, and maybe I should somewhere start listing the wonderful properties of the fusion method. I mean, it's not so important, so you don't, but you don't have to see it. Maybe I'll bring it here. So, okay, let me state the other meta theorem first. By meta theorem, I mean it's not a theory, you have to instantiate it. So there are many meta theorems like this, and they are here, and I'll say more about them in a second. And the other meta theorem, which is a sort of, became clearer and clearer with every paper, which was sort of mind-blowing, is that in many cases, is at most, well, so in some cases it was like you get a constant, you get a constant power here, but in some cases you even get a constant power, just linear. It's really tight. So it just characterizes this kind of thing, really characterizes. If you choose your omega right, it can characterize the size. And I want to tell you, in the time, so everybody is clear. So first of all, it provides a lower bound that's sort of immediate from the definition, sort of the definition gives it. But this, in lots of cases, this lower bound is tight. Okay. And this should start, making it really interesting. So in what sense? I want to write here some properties of the fusion methods. And the most important one to me is that it's static. What do I mean by static? There's no circuit here. There's just a cover problem. The kind of, these abstract gates are unordered, right? In order to, right? They are unordered, and nevertheless, I give you a cover, and you can put these unordered gates together to form a real circuit. That's what this means. And I want to dispel not quite dispel. I want to challenge you to check it for the various examples I'll give. I want to tell you why it's, what is the algorithm? How do you construct, what is a circuit constructed from this abstract set of gates? So you get an amorphic set, which is unordered, and you just take it and create from it a circuit using the same operations that actually is ordered and is completely according with a straight line program for the for this thing. So how do you take something like this, which is GI, HI, operation I, this set of size T, and you create from it a circuit, or really a circuit or straight line program, which also has size T or polynomial in T. So really bizarre. But the answer is like lots of things in life, you don't know what to do. The best strategy to start with at least is a greedy algorithm, right? And the greedy algorithm works, at least in all the cases I know. Of course, it's a meta theorem, it's not but the greedy algorithm works. It's like in resolution, when I give you a bunch of contradictory clauses and you want to prove it's a contradiction, you want to derive the empty clause. How do you derive the empty clause? Well, you start doing everything you can. These two implies another one. These two imply another one. Then you just, repeat this greedy until, well, either you cannot generate any more clauses or you reach the empty clause and you get a contradiction. Also here, you are doing the same thing. Only it looks very bizarre because these objects are doubly exponential in size, or maybe triply exponential, I'm not sure. They are huge, so you're going to create a circuit out of them. And the main point is that when you're creating the circuit, you don't have to specify all these things. All you have to specify is the value of f on them. Because the cover problem tells you that an input is this, so the key to proving this is that f of z, but just by definition, f of z is 1 if and only if there exists an f. There exists an f such that, for all the GI, for all these, all the GIs that appear there, f of GI op I, HI op I, op I is GI op I. That's all you have to do. So all you have to do is just solve this search problem. Does there exist such an f? And even though f lives in a double or triply exponential space, all you have to do is specify it on these guys. Well, you have it already specified in some places, right? It's specified here, specified, right? You know that it's specified on 0, on 1, and on the variables. And then you start looking, these are, maybe xi is one of these guys. It will be. Maybe, and then you just try to force it in a greedy way. Try to assign values to f in a greedy way. And one of two things will happen, just like with the resolution proof. Either you can keep fixing it, and you'll get a consistent values of f, and then you have proven this. Or you get stuck, and then, just say it in the right direction, yeah. You get stuck, you cannot complete it, and then it must be a 0 because such an f doesn't exist. That's it. And I should stress this if and only if I proved only one direction. But you should know that an f exists for one of the function simply by taking the singleton row that computes the, if f here just selected the value of the input you have, which is a one of the function, this would be a legal computation. Okay, so that's the amazing thing, and now the question is, questions about this. This is like the key thing. Yeah?
Can you describe more carefully what you mean by cover exactly?
Well, these are all possible f's here, right? And each one of these guys is a subset of all possible f's, right? So you're trying to take a few sets like that, abstract gates, if you will, to cover this space. This is it. You're not supposed to, succeed if there's a small circuit.
So is there a way to, say, write all of this in proof-theoretic language, say?
You can, but this is a combinatorial statement. You can try to address it in any way you like, but this is a combinatorial set cover problem. There's a finite set, there are finite collection of finite subsets of it, and you ask how many of them do you need to cover. Yeah. So let me tell you in the last few, yeah.
So properties 1, 2, and 3 do not have the parameter t. So I don't understand why.
Yeah, but rho does. Rho is the smallest.
The top phrase there exists an f satisfying 1, 2, and 3 implies size f greater than t. It's the very top sentence on that board.
Yeah.
I don't understand why that's true.
Yeah, because we applied, we sort of, okay, maybe I didn't write it correctly. The row is clear, right?
Yeah.
Yeah. So that's all I mean.
Okay.
Yeah, that's all I mean.
So
Yeah.
I think one thing that was confusing me, maybe that motivated my question earlier, is what is the scope of for every GH in condition?
Yeah, these are Boolean functions, but they are restricted only to the part that you see in this matrix. So this for all Boolean functions, 0, 1 to the n to 0, 1.
So, right. So,
but if you pick your U to be a small subset, then you may not see, they will be partial. So you just think of them
as functions from U to 0.
Yeah, as from U to 0.
But is it all functions from U?
It's up to you. It's up to you.
No, but it's the ones that happen to appear in the...
Yeah. So you fix U, and then these are functions from U to 0, 1.
But... Okay. But now, when you're talking about a cover, you're allowing yourself to pick, you're not fixing U in advance.
Yeah, so, I mean, this, I define it in such a way that you can try to prove lower bounds for various f's. Yeah, so these are sets that have elements not in your omega f, but that's okay. You're trying to cover, the sets that you use, may not be fully contained in omega f. So for the parts you don't use to cover it.
So, but now I have the same question Ryan has. So if it works for every U, every function from U to 0, 1, where do you use that t is small?
In this cover.
Is the cover, the cover is the smallest t, such that
No, I meant just in the conclusion that f has size. Why don't you just get the conclusion that f has size infinite?
So Avi, is U parameterized by t? Because it looks like your U depends on t, right? Because U is the set of all straight line computation you have using t.
U is just a subset of the ones of the function.
And it was just computed by a straight line program size t.
Yeah, it is computed by, but that's right. So you assume
U should have a subscript t, right? Is all the straight line
U doesn't have to have a subscript t. Let's push this. I want to tell you just about we can have a discussion about this. I just want to tell you the most important thing is the versatility here. So there are lots of properties that I like, but I want to talk about the versatility. And let me create a little table, and that will... Well, maybe I want this.
Cover of the absolute solution, so we can put this in this space.
I want to just say in what cases the second meta theorem works, so you'll see how important the flexibility of choosing what omega is. I mean, one might think that, why should you restrict yourself in omega? In the functionals you allow yourself to apply. You might as well apply all of them, and then it's a harder cover problem, and you'll get better lower bounds. However, of course, we know as low-bound provers that often restricting yourself helps, and maybe smaller sets or nicer sets work. So let me have a table here of what omega is. The model, you'll see what I mean by model. It will be the gates and the class it characterizes in terms of the second meta theorem. So Rasborov in all his papers took omega to be the monotone filters. So he's allowing only f's which are monotone functions. Why? It's convenient for him, and that's what he does. And for those of you who know, there's an analogy to ultrafilters that plays in maybe in his mind, certainly in Karlsberg's mind, as you see. So in the 3 papers I mentioned of Rasborov, so these are all Rasborov, he looks here at, so I want to say circuit model, and I want to say here a non-deterministic branching program model. So the only difference between a circuit model and a non-deterministic branching program model is that when you are looking at how a straight line program behaves, I mean, some of you will get it and some of them you will not, but in the branching program model, one of these functions have to be a variable. That's the only thing that distinguishes a branching program from a circuit. You take 2 things, but one of them has to be a variable, then what you get is really a non-deterministic branching program. So I don't have time to define it, so I'll just say it. But the amazing thing, so here is the monotone case, here is the non-monotone case, and here again is the non-monotone case, but it's a branching program. And it shows that the meta theorem here characterizes monotone P. The second result, which I mentioned, is that the general approximation method characterizes P. I mean the non-uniform. You can write P/poly wherever you like. And this characterizes non-deterministic branching program completely. The cover problem, so you don't lose anything by moving from this dynamic ordered computation into the unstructured branching program. In the Karchmer paper, he looks at self-dual filters. What are self-dual filters? They are monotone filters, but if you have, for some set, you get a 1, so think of these columns as just representing sets. Well, anyway, if you take a vector and this f gives you 1, when you complement this vector, you want to get a 0. That's a self-dual function. And he restricts himself to this for good reasons, because it's easier to argue about. And here's sort of an amazing thing that he gets. He shows that if you look at non-deterministic circuits, then what you get, so it can have non-monotone circuits, but non-deterministic. I should say, non-deterministic model is very easy. You also add here not just the x's, but you add a few variables here that are sort of, they are not given. They could be anything. But when you apply this functional on it, it will give you other nonce. So this is like the witness. It will also give you a witness. So it's very, very general in this way. And it proves that this characterizes NP. And in our paper with the we have 2 papers. So I'll just, this is the last minute. So in one paper with Maurizio, we decided to look, instead of self-dual filters or functions, we decided to look at affine functions. So here you want to look at affine functions where the circuits have parity gates. it's very nice that you know, your function will do, at least will be sort of trivially give you one of these commutativity conditions. So if you have a monotone field, you ask why monotone is good, because you don't have to check the or condition, you just have to check the end condition. If you take things to be affine functions, then you don't have to check linear gates, you just have to check the end. So we looked at this, and we looked at non-commutative circuits. So it's a very different family of functions. It's just affine functions, and there are just exponentially many of them, as opposed to self-dual functions or monotone functions, where the doubly exponential functions. There's non-commutative. What do you think? What class do you think this would characterize? So the open question, yeah, I have to finish, but you know, explain this. I mean, we don't understand. And when you look at other affine, and you look at branching programs, then you again characterize, well, here you characterize parity L, so the counting version of L. And the final thing I want to say, again with affine, the nice thing when you are trying to explain how this algorithm in the second meta theorem works, what is exactly the search problem that you are trying to solve in building a branching program from an abstract collection of gates, we realize that you get a new model, and this is the span program. So it arose just out of there. Of course, many of you know why it's useful in lots of other things, like secret sharings and quantum computing and Avishai's work on shrinkage and so on. But it creates a new model. So let me summarize this by saying that I believe that because it does characterize complexity classes, it can prove lower bounds. It's subjected to the natural proof barrier only if you prove the cover lower bound using natural techniques. But Razborovin is lower bound here of the log n, whatever it is. Log star n uses Ramsey theoretic techniques, and you know, they look like they go beyond that. So, yeah, you have a full semester prove lower bounds. Thank you. Yeah.
Sorry, are you claiming that some of these lower bounds can be rephrased in this language?
Yeah, all of them. All of them. All of them, and Maurizio is doing some, and yeah, so the others are sort of new. Yeah, absolutely. Maurizio in his paper, the first paper, rephrases the monotone click lower bound in this language. And it's very beautiful. And his second part, where he looks at the Sipser result, he rephrases his result on countable non-deterministic circuits, namely analytic is different than co-analytic, in this language. And there you can really use ultrafilters. It's very convenient to use ultrafilters. It's not a different proof. In both cases, it's not a different proof than the original, but it's, you know, it's nice. And in the case of Sipser's proof, it's especially nice because Sipser proofs is, you know, it's really a diagonalization argument. It's not so difficult. Anyway, it's a diagonalization argument. But if you do it with ultrafilters, you know, the limit, you know, it provides a sense of limit that's much more liberal than limits that we learn in calculus classes. Yeah. More questions? Yeah.
So in the choice of omega for the monotone field over bounds,
for which lower bounds?
So for the monotone P lower bounds, you could take omega to be all functions, right? From 0 to
yes, you could.
So it would be just made the lower bound harder.
Yes, but yeah, so it's always better to take a bigger omega. But, you know, you want to, you know, in your lower bound argument, you have to argue about omega. And in some cases, argue about a simpler omega is more convenient. It just happens to be more convenient. In the case of, you know, these actual lower bounds, both here and there is a similar lower bound we prove for branching programs or parity L, you know, you simplify, I mean, omega is affine and you even simplify it further. So in this paper that I wrote, the survey on the fusion method, that's also in the abstract, There are concrete combinatorial questions that arise from there where you don't have to think about any omegas or anything else. It's just very concrete combinatorial questions. Lower bounds there will give you circuit lower bounds in various models.
Okay, so let's thank Avi again.